okay, milliwatts. Anybody think why it's only 5? Usually the switching activity is gonna dynamics gonna be a lot more uh, than the leakage, right? I mean, than the internal power, right? This is only supposed to be about 10%. And anybody think of the reason? You can just put in the chat. I'll give you a few minutes to think and this why the switching is only 5 versus internal. Anyone take a stab at it? Yeah, just a little bit. Okay, so no one. All right, the reason is remember clock tree is a big portion of the switching, right? So in placement, we don't have the clock tree yet. So the clock tree is there's no clock tree. That's the reason why the leakage is currently low. So when we build the clock tree, expect these numbers to grow up to be a lot bigger. Okay, so here the leakage dominate. Okay. So here it breaks, just give you a breakdown difference between sequential, macro, IO. Our design don't have any IO, so you can see there's none. So sequential basis flip-flops and combinatorial logics is and or gate and so on. So it did give you a breakdown, pretty detailed. So this is just a summary. So you'll see this in the lab. Okay. Okay, so next topic is power optimizations. So what happened during power optimization? Okay. Um, so we're swapping cells. First is swapping cell for lower power. So basically, you have usually happen is when you do power up, usually it does it on a non-critical nets. So meaning that nets that has extra margin is going to try to downsize. So you have like a AX going to try to downsize to a 4X, or a low VT is going to swap for a I mean, a high VT is going to swap for a low VT is going to swap for a high VT. So where you don't need the speed, but you need to reduce power. Also, it'll delete some of the buffer inversion if it can still meet DRVs. So this is just another set of commands here. We have to set input switching activities. Okay, here we set a global and activity is 20%. So meaning that 20% of the everything's gonna switch at 20% of the time out of one cycle. It's gonna switch 20% of the time. And sequential activities is flip-flop. Flip-flop usually switch more because it's connect to the clock tree. So assume it's 80% of the time. So maybe not, maybe too pessimistic. It depends your design, right? So this is an early guesstimate or estimate. Okay, here I have a command here says set DB obligates to dynamic, basically telling it to optimize 50% dynamic and 50% leakage. Actually, at this stage, since there's no clock, we could just do all leakage, right, and set it to 1. Okay. Well, this is just a repeat. Okay, so to run power up in Innovus, you just do up underscore power dash pre-CTS after you set your activities, and you should be able to generate the report. Actually, you'll be able to see the tool does the power up. So this is the log of the power ups. As you can see, what's happening here. As it commits, meaning that it make changes, right? So you can see this memory real in Slack. So the Slack still met, and density is 55. Okay. So at the end, you have to do report power to see what the power number would be. So this is just a log from Innovus.
chip is not operational. Power is being saved and optimized because it impact your performance, right? Your chip performance. So can anyone tell me which power component of power is the most important to be optimized for? Is that internal power in here, switching power, leakage power, or total power? Can you just, what is the most important one? Can you type in the chat which component is the most important to optimize for handheld applications?
And by the way, most of the